For a system in a time-independent potential, the time-dependent wavefunction can be written as a spatial function multiplied by a temporal phase factor with certain frequency. The spatial function is called a time-independent wavefunction, corresponding to a stationary state. The frequency of the temporal phase factor is determined by the energy through the Planck's relation. In other words, each stationary state has a certain energy. Substituting this expression for the time-dependent wavefunction into the time-dependent Schrödinger equation yields a simpler time-independent Schrödinger equation. It is particularly important as it simplifies the task of solving the time-dependent Schrödinger equation for any state. A time-independent Schrödinger equation may give many possible energies. These energies are known as energy levels, or simply, levels. A level is degenerate if it corresponds to two or more different stationary states of a system. Conversely, two or more different states of a system are said to be degenerate if they have the same energy. The number of different states corresponding to a particular energy level is known as the degree of degeneracy, or simply, degeneracy, of the level. The ground state of a system is its stationary state of the lowest energy. An excited state is any state with energy greater than the ground state. The particle in a one-dimensional infinite quantum well is the simplest system where the Schrödinger equation has analytical solutions. That is, the energy levels and stationary states can be found exactly. The infinite well is defined as having zero potential energy inside a certain region and infinite potential energy outside. It is impossible to find the particle outside the well, because the particle must have a finite energy. Thus, the wavefunction is zero outside the well. Only the time-independent Schrödinger equation inside the well needs consideration, where the potential energy is zero. It is a typical second-order ordinary differential equation. The general solutions are sinusoidal functions. Here, the energy is related to the wave vector. This relation is compatible with de Broglie's relation and non-relativistic kinetic energy. A and B are arbitrary constants if there is no additional condition. However, in this particular system, A, B and K are determined by the boundary conditions. The time-independent wavefunction must be continuous. Thus, at any boundary of the well, the wavefunction inside the well must be equal to that outside the well. For example, at x equals 0, psi equals 0, so B equals 0. At x equals L, psi equals 0 as well. However, A is not 0 as the wavefunction cannot be 0 everywhere. Therefore, KL must be an integer multiple of pi. This integer is the quantum number. Negative values are neglected, since they give wavefunctions identical to the positive ones. The values of K are discrete. This discrete K implies discrete energy levels. Furthermore, the levels are all non-degenerate. The unknown constant, A, may be found by normalization condition. That is, the total probability of finding the particle in the space is 1. Finally, the time-independent wavefunction is found, which depends upon the quantum number. The time-independent wavefunctions of the first three states are shown here. Their wavelengths are 2L, L, and 2/3 L respectively. The probability densities depend upon the wavefunctions. For any value of n greater than 1, there are regions called spatial nodes within the well at which the particle cannot be found. The number of nodes is n-1. The time-dependent wavefunctions oscillate like standing waves with their frequencies related to the energies. For example, the ground state is given by n equals 1. It has the lowest wave vector, that is, the greatest wavelength. It also has the lowest frequency due to its lowest energy. The first excited state is given by n equals 2. It has twice wave vector and half wavelength of the ground state, as well as quadruple energy and frequency of the ground state. The second excited state is given by n equals 3. It has triple wave vector and 1/3 wavelength of the ground state, as well as 9 times energy and frequency of the ground state. If a particle is trapped in a two-dimensional well, it may freely move in the xy plane, between barriers separated by lengths Lx and Ly respectively. The kinetic energy in two-dimensional space is a Laplace operator. The stationary states and their energies may be calculated using a similar approach to that of the one-dimensional well with the help of separation of variables. Here, nx and ny are quantum numbers. There are two quantum numbers because the particle has 2 degrees of freedom in motion. The ground state is given by nx equals ny equals 1. It is non-degenerate. If Lx equals Ly, the first excited level is given by nx equals 1, ny equals 2, or nx equals 2, ny equals 1. It is doubly degenerate, degeneracy 2. The second excited level is given by nx equals ny equals 2. It is non-degenerate. And the third excited level is given by nx equals 1, ny equals 3, or nx equals 3, ny equals 1. It is doubly degenerate again. If a particle is trapped in a three-dimensional box, it may freely move in the xyz space, between barriers separated by lengths Lx, Ly, and Lz respectively. The stationary states and their energies may be calculated using a similar approach to that of the two-dimensional well. Here, nx, ny and nz are quantum numbers. There are 3 quantum numbers because the particle has 3 degrees of freedom in motion.